cluster. They're the ones that are embedded in that sea of dark matter that are causing the bending of the light to cause these optical illusions, or mirages, practically, of the background galaxies. So the streaks that you see, all these streaks, are actually distorted images of galaxies that are much further away. So what we can do then is, based on how much distortion we see in those images, we can calculate how much mass there must be in this cluster. And it's an enormous amount of mass. And also you can tell by eye, by looking at this, that these arcs are not centered on individual galaxies. They are centered on some more spread out structure. And that is the dark matter that is in which the cluster is embedded. Okay? So this is the closest you can get to kind of seeing at least the effects of the dark matter with your naked eye. Okay, so a quick review then, okay, to see that you're following. So the evidence that we have that a quarter of the universe is dark matter, this gravitationally attracting stuff, is that galaxies, the speeds with which stars orbit in galaxies is much too large. It must be embedded in dark matter. The speed with which galaxies within clusters are orbiting is much too large. It must be embedded in dark matter. And we see these gravitational lensing effects, these distortions that say that, again, clusters are embedded in dark matter. Okay, so now let's turn to dark energy. So to understand the evidence for dark energy, we need to discuss something that Stephen Hawking referred to in the previous session, and that is the fact that space itself is expanding. So if we imagine a section of our infinite universe, okay, and so I've put down 4 spiral galaxies, okay, and imagine that you put down a set of tape measures. Okay, so every line on here corresponds to a tape measure, horizontal or vertical, for measuring where things are. If you could do this, what you would find that with each passing day, each passing year, each passing billions of years, okay, the distance between galaxies is getting greater. And it's not because galaxies are moving away from each other through space. They're not necessarily moving through space. They are moving away from each other because space itself is getting bigger. Okay? That's what the expansion of the universe or space means. So they're moving further apart. Now, and what Stephen Hawking mentioned as well is that after the Big Bang, space expanded at a very rapid rate. But because gravitationally attracting matter is embedded in this space, it tends to slow down the expansion of the space. Okay? So the expansion slows down with time. So in the last century, okay, people debated about whether this expansion of space would continue forever, whether it would slow down, it would be slowing down but continue forever, slow down and stop, asymptotically stop, or slow down, stop, and then reverse, so it would start to contract again. So a little over a decade ago, 2 groups of physicists and astronomers set out to measure the rate at which the expansion of space was slowing down. Okay? By how much less is it expanding today compared to, say, a couple of billion years ago? The startling answer to this question, okay, from these experiments, was that space is expanding at a faster rate today than it was a few billion years ago. Okay? So the expansion of space is actually speeding up. This was a completely surprising result. There is no persuasive theoretical argument for why this should happen. Okay? No one was predicting ahead of time this is what's going to be found. It was the opposite of what was expected. So we need something to be able to explain that. Now it turns out in the mathematics, you can put it in as a term that's an energy, but it's a completely different type of energy from anything we've ever seen before. We call it dark energy. And it has this effect of causing space to expand. But we don't have a good motivation for putting it in there at this point. Okay? So it's really unexplained as to why we need to put it in. Now, so at this point then, what I want to really emphasize to you is that, first of all, dark matter and dark energy are completely different things. Okay? There are really 2 mysteries out there as to what makes up most of the universe. And they have very different effects. Dark matter, because it gravitationally attracts, it tends to encourage the growth of structure. Okay, so clusters of galaxies will tend to form because of all this gravitational attraction. Dark energy, on the other hand, is putting more and more space between the galaxies, makes it the gravitational attraction between them decrease, and so it impedes the growth of structure. So by looking at things like clusters of galaxies and how they, their number density, how many there are as a function of time, we can learn about how dark matter and dark energy compete against each other in structure forming. In terms of dark matter, I said that we don't have any really persuasive argument for dark energy. Do we have anything for dark matter? And the answer is yes. We have well-motivated candidates for the dark matter. Now, what do I mean by well-motivated? I mean that we have mathematically consistent theories that were actually introduced to explain a completely different phenomenon, okay, things that I haven't even talked about, that each predict the existence of a very weakly interacting new particle. So this is exactly what you want in physics, where a prediction comes out of a mathematically consistent theory that was actually developed for something else. But we don't know if either of those are actually the dark matter candidate. Okay, one or both, who knows? Or it could be something completely different. Now, we look for these dark matter particles because, after all, they are here in the room, okay? And they didn't come in the door. They just pass through anything. They can come through the building, through the earth. They're so non-interacting. So one way to look for them is to build detectors that are extremely sensitive to a dark matter particle coming through and bumping it. So a crystal that will ring if that happens. So one of my colleagues up the road and his collaborators have built such a detector, and they've put it deep down in an iron mine in Minnesota. Okay, deep under the ground. And in fact, in the last couple of days, announced the most sensitive results so far. They haven't seen anything, okay, but it puts limits on what the mass and the interaction strength of these dark matter particles are. There's going to be a satellite telescope launched later this year, and it will look towards the middle of the galaxy to see if we can see dark matter particles annihilating and producing gamma rays that could be detected with this. The Large Hadron Collider, a particle physics accelerator that will be turning on later this year. It is possible that dark matter particles might be produced at the Large Hadron Collider. Now, because they are so non-interactive, they will actually escape the detector. So their signature will be missing energy. Okay? Now, unfortunately, there's a lot of new physics whose signature could be missing energy, so it'll be hard to tell the difference. And finally, for future endeavors, there are telescopes being designed specifically to address the questions of dark matter and dark energy, ground-based telescope, and there are 3 space-based telescopes that are in competition right now to be launched to investigate dark matter and dark energy. So in terms of the big questions, what is dark matter? What is dark energy? Big questions facing physics, and I'm sure you have lots of questions, which I very much look forward to addressing over the next 72 hours while I'm here. Okay? Thank you.